Hello, and welcome to my Lab 4 presentation, a macroscopic view of DC and RC circuits. My name is Anand Jha. Let's begin. To introduce this lab and to state its main purpose, this lab asks us to use the CCK to virtually model circuits on our computers. It wants us to determine how circuits behave with resistors in both series and parallel, and use multimeters and ammeters to measure the potential difference in current across a circuit. Finally, it wants us to analyze the effects of a capacitor in a circuit and calculate its time constant. Some fundamental principles that this lab will go over is Ohm's law, which states that V equals IR, voltage equals current times resistance. It also talks about Kirchhoff's two laws, the first law being the junction rule, which states that the sum of all currents entering a junction must equal the sum of all currents leaving a junction. And the second law, which is the loop rule, which states that the sum of changes in potential energy around any closed loop must be zero. It will also talk about how in capacitors delta V equals Q divided by C, which we can use to derive the equation ln of delta V divided by delta V naught equals negative T divided by RC, an equation we will use to calculate the time constant for our capacitor and ohm light bulb. So to describe the experiment itself, the experiment will ask us to determine how much current flows through a circuit with two resistors in series, one resistor with a resistance of 47 ohms and the second one with a resistance of 100 ohms. It will also ask us to graph the potential versus position around the circuit and add the values up. Hopefully this addition will give us the value 0 by Kirchhoff's rules. It will also ask us to determine how a circuit is altered when a voltmeter is added in parallel and how it is altered when a ammeter is added in parallel. It will also ask us to determine how long it takes for a capacitor to both charge and discharge with light bulbs of different resistances, and it will ask us to determine the RC time constant for a capacitor and light bulb circuit. So the observations and data that we got from this lab are that the current equals the voltage divided by the total resistance, which makes sense by Ohm's law, where the total resistance in a series circuit equals R1 plus R2, so 147 ohms for our circuit. We also saw that the potential around the circuit always added up always equals 0 by Kirchhoff's rule, and we saw that when we place our voltmeter in parallel that it doesn't alter the circuit in any way, but when we add our ammeter in parallel, it actually increases the current flow across the circuit. The voltmeter, since it has an infinite amount of resistance when added in parallel, no current would flow through it, therefore essentially doesn't even create a branch. However, an ammeter has zero internal resistance, at least in our simulated model, therefore when added in parallel, it drastically decreases the total resistance of the circuit and increases the current flowing. We saw that our capacitor takes 20 seconds to charge and discharge with a 10 ohm light bulb and 40 seconds to charge and discharge with a 20 ohm light bulb, so we can see a linear increase. Also, we got an experimental value for our RC time constant of about 6.034 seconds, very close to the theoretical 6-second value. Here are some images that describe our experiment. In the top left, we can see that we get 0.02 amps for our circuit with 147 ohms total resistance, but that increases to 0.06 amps when we add our ammeter in parallel, as the ammeter has zero internal resistance. We can also see in the bottom left the graph, which shows that our final voltage at the end of the loop is equal to 0 volts, which satisfies Kirchhoff's rule. And we can see on the right hand side with our data of ln V divided by V naught versus time in seconds, when graphed would give us a linear graph with a slope of -1 over RC. So in conclusion, we determined that ammeters, wires, and batteries have no internal resistance in our simulated model, whereas voltmeters have an infinite amount of resistance. We also saw that the voltage drop over a resistor in a circuit is equal to the current flowing in the circuit times the resistance of the resistor. We also saw that the experimental value of our RC time constant is nearly identical to the theoretical value. Some additional questions that we can ask for this lab is, what if we had done this lab in real life? What would have changed in our circuits? For one, the current measured would have been lower, as there would have been internal resistance in the ammeters, the batteries, and the wires, increasing the total resistance of the circuit and decreasing the current flowing through the circuit. Also, we would have seen our circuit being altered when our voltmeter was attached in parallel, as a true voltmeter does not have infinite resistance, and therefore some current would flow through it. Also, our experimental value of RC would be further away from the theoretical value, as in real life there would be, again, internal resistance of the wires, and it would be much harder to to properly acquire the values and graph them. Secondly, and lastly, what if we were doing this live in real life and used a real battery to charge the capacitor? How quickly does the ideal model predict this would take, and how long would it take in reality? The ideal model actually predicts that the capacitor will be fully charged instantaneously, but this is incorrect as the battery and the wires would both have some internal resistance, causing it to take some amount of time, but a very small value. Thank you for listening to my lab. I hope you enjoyed.